Good afternoon and welcome to our webinar on probabilistic latent factor induction with Bayesian networks and BayesiaLab. I'm really glad that you've decided to join us this afternoon. And despite this somewhat wordy title of our webinar, we have had an enormous sign-up rate for our event today. Perhaps it was actually the biggest number of registrations we've ever had. So let's talk about what's in store for today. Here's our program. First, we'll talk about our team and our technology a little bit. After that, we'll enter into the world of psychology, and we'll talk about personality models and how they reduce the dimensionality of character attributes. After that brings us to the question of what this has to do with Bayesian networks. We will talk a little bit about nomenclature and terminology, and then talk specifically about arc force as a very important measure for our purposes today. Once we've established these basics, we'll go straight into the workflow with BayesiaLab. So the introductory part should probably take around 20 minutes or so. After that, we would spend approximately 40 minutes on the actual workflow. That's going to be the main part of our webinar today. So this is our team for today. Let me start off by introducing the ladies. In the center of the slide, you see Stacy Blodgett, who is our Director of Customer Engagement. On the right, you see Claire Gora, our Director of Sales. And finally, my name is Stefan Conradi, and I'm the Managing Partner of Bayesian USA, and I will be your program host for today. So, while our marketing team is based in North America, Bayesia's headquarters and the development team are based in Laval, Laval in France, that is, roughly 150 miles or so southwest of Paris. Bayesian was formed by two professors working in the field of artificial intelligence, Dr. Lionel Jouve and Dr. Paul Monteanu, who are still heading the company today. And our principal product, BayesiaLab, directly emerged out of their research at the time. So as you can see, BayesiaLab has now been under development for nearly 20 years. And what started out as a little tool has now evolved to become a very comprehensive software platform, including our principal product, BayesiaLab. We have academic editions, web simulators, APIs, etc. It has become an entire, software platform involving desktop software, web applications, and APIs. But today you will only see BayesiaLab Professional, our core product. Now, many of you know that we have customers around the world, but today I think in particular I'd like to highlight one of our customers, and that is Procter & Gamble, because our collaboration with them has really driven the workflow that you're going to see today. This factor analysis, latent factor induction workflow was really driven by some of their research need. In that sense, what you see today is very much industry practice. Now, as always, we can only touch on so many details, so our book remains an important resource. In particular, chapter 8 of our book discusses a process quite similar to what we're showing today. Not entirely the same, different data set, but still a lot of the basic concepts remain the same. And as always, webinar slides, data, and the recording of today's event will become available either later today or perhaps tomorrow. So that brings us to our background and motivation. Now we're talking about the dimensions of human personality. Now, when you look it up in a dictionary, or actually, let me just go back a step. when you look it up in a dictionary, personality refers to the combination of characteristics or qualities that form an individual's distinctive character. So that's the official definition. And as we all know, we tend to be very quick to judge the character of others. In fact, we probably all have lots of vocabulary in our heads that all deals with personality and how we can describe others. What I find quite interesting, of all the 600 terms that you see here on this slide, roughly half of them are negative, whereas only 1/3 is positive. It's quite interesting. And supposedly there are 18,000 words in the English language that are related to personality. Now, I find it hard to believe, and my vocabulary certainly isn't that big, but I think we would all agree that there are lots of terms that describe the many facets of the human mind. Now, authors of novels, perhaps, they can use many of these fancy words to illustrate a narrative. And one could perhaps argue that, yeah, each of these 600 terms that we saw represent a single dimension. But I think for scientific investigators, that's probably not at all manageable. They need to reduce it and take perhaps a much more systematic approach to the human mind, to the human personality. So let me just share with you a couple of models that are out there that are perhaps popular among psychologists, and please don't get me wrong, I'm not claiming to be an expert in this domain. I've simply Googled some of these topics and hope that these can illustrate our methodology that I'm going to share with you. So here's one model, Eysenck's model of personality, which consists of 3 main dimensions: psychoticism, extroversion, and eroticism. Another one that's perhaps what it seems the most popular one among many of these models, that's the so-called 5-factor model. And that includes openness, conscientiousness, extroversion, agreeableness, and neuroticism that we also saw in the earlier model. And there have been various iterations of this model that have been developed since the 1960s. Now, more recently, an alternative model has been proposed by Lee and Ashton, and as the name Hexaco implies, this model includes 6 dimensions, which are honesty, humility, emotionality, extroversion, agreeableness versus anger, conscientiousness, and finally openness to experience. So, and to identify where you stand with regard to all these 6 dimensions, there are questionnaires that have been developed, and specifically for this Hexaco model, 240 questions were compiled that are all linked to one of these 6 dimensions. And you can find different versions of this personality inventory online. Of course, they are also administered in a clinical setting more formally, but you can go online and actually take these personality tests yourself. And we will be using one of those public data sets, one of these public questionnaires, as the input for our analysis today. What's worth pointing out, all variables, all questions, or all statements, these are not really questions, but rather statements that you can disagree or agree on a scale from 1 to 7. And this is consistent with regard to all the 240 statements. Now, this particular personality inventory, along with many others, is hosted on the open source psychometrics project. And what's really good for us is that all the responses that are collected are made available to the general public for download. So more specifically for the hexacode data set, we have approximately 15,000 respondents who have answered all 240 questions. And that will be our data source for today. Needless to say, the data we're now using is not generated through a clinical setting, so we're not going to generate any deep new insights into psychology. But as I said earlier, I think we can use that data set still to illustrate our methodology. So what exactly do we want to do today? To put it casually, we want to perform an exploratory factor discovery. We want to discover latent, hidden concepts. And here I've shared with you on this slide the Latin etymology of latent. And I'm really emphasizing this to convey its meaning, or to emphasize its meaning, that we're really trying to uncover concepts that have not been directly observed, that are not directly observable, but that we have to generate from other observations. Now, of course, we would like these factors that we discover to be easy to interpret and meaningful. And we want what is contained in these factors to be homogeneous, so they're clearly distinguishable. We want to discover stable dimensions. So as we, repeatedly perform such an analysis, perhaps on new data, we would recover similar dimensions, similar factors. And of course, as we generate factors, as we reduce dimensions, we want to be careful about it so that we're not losing too much of the underlying information. So we're not dumbing down the original raw data. And finally, of course, all this should be computationally tractable, because given the number of dimensions we have, this could potentially be a big task. So dimension reduction. So that's really important, and this illustration is just to emphasize, really, we want to be careful. We want to maintain as much as possible of the original richness in the data without compressing or condensing it so much that we lose some of the detail. So that's where we need to be careful. Now, why Bayesian networks in BayesiaLab? You know the saying that to a little boy with a hammer, everything looks like a nail. That's how we are. Everything we see, any research topic, we see a Bayesian network in it. But perhaps to you, it's not as obvious as to us. And so let me talk a little bit about Bayesian network, just for a brief moment, at least for those who are perhaps relatively new to Bayesian networks. Bayesian networks were invented by Professor Judea Pearl, who's been teaching and researching at UCLA since 1970. And he wrote his first paper on Bayesian networks back in 1985 or so. And since then, Bayesian networks have evolved into a fairly comprehensive paradigm that has been widely used within computer science. But only in the last decade or so have Bayesian networks spilled over into other fields of research. And that's something we very much like to encourage, because we think Bayesian networks are very, very powerful as a kind of a very explicit research framework that we can work directly with and study complex problem domains. So what we've done, and I'm now speaking of Bayesian, we've taken this mathematical formalism and translated it into a research software, or we could say a research workflow. And typically, this workflow involves that we generate a Bayesian network model either through knowledge modeling, whereby we directly encode any domain knowledge that we may have, or we machine learn a network from data, or we may do a little bit of both. Once we have the network, then we can analyze, simulate, manage risk, diagnose, optimize, all kinds of things, very often to support decision making, etc. And this is our software, BayesiaLab. You will see it live in action shortly. That's our software that allows you to do that through a very elegant graphical user interface. You can encode networks, learn them, edit them, perform inference, analyze, simulate, optimize, all on the framework of Bayesian networks. So let me talk a little bit about nomenclature, because it can easily get confusing with clusters and factors and manifest and so on. So I've taken here 5 variables from the Hexaco personality inventory. And these are, each node here represents a variable. In the Bayesian network framework, we call them nodes. That was actually observed. So these were values that were recorded through the questionnaire, through the personality inventory. Because they were observed, we call them also manifest. So they exist. And what we see here, what I'm showing now, is what we call a monitor. That is a feature in BayesiaLab that shows us the distributions of the states. Given that the questionnaire had a 1 through 7 rating for all variables, we see that distribution, or we see 7 states, along with a bar chart that tells us for each node how frequently this state was chosen in the response. So these are our manifest variables, and of course we have 240 of them. Now, what we have yet to create is a factor, the unobserved variable, the latent variable. Sometimes we refer to it as the cluster variable. That's what we're going after. That's what we want to generate. And beyond just introducing it as a concept, we will need to generate actual values for this newly created factor variable. Here, you will see what the end product will look like. We will have a distribution with states and values for the factor. And later on, we will see how we will see the monitors that are associated with the factors and show us their distributions. So one thing that will be helpful beyond the short acronyms that define the variables, we also have long variable comments, sort of long variable names that help us understand what that question, what that statement was all about. So now you've perhaps seen how we have machine learned very elaborate high dimensional models with BayesiaLab to capture complex problem domains. But today we don't really want, or we don't really need, we don't want all these dimensions. So how does that fit with our objectives of reducing dimensionality? So there are several concepts that emerge, or several measures that emerge directly out of Bayesian networks that will be tremendously helpful with regard to finding factors, discovering factors. And the measures are of an information theoretic nature, and we get them by virtue of having machine learned a Bayesian network, and BayesiaLab can pretty much automatically compute these values, these measures for us. That includes entropy, mutual information, arc force, node force, and several others. But for us today, it's really the arc force that is absolutely critical. That will be our crucial concept that allows us to do this factor analysis, this factor exploration. So we will talk about about arc force very extensively. So now arc force, I have to admit, that is our name. arc force is a measure of arc importance, but it is really more formally known as Kullback-Leibler divergence. That's the information theoretic term. And what it stands for is it measures the difference or distance between two joint distributions. For instance, a distribution Q and a distribution P. And but this is, let me explain this with a network. Here we have a small network, a machine learned network, which involves some of the variables from the hexaco inventory. And let's say we call this network P. So this network represents a joint probability distribution. And as we know, Bayesian networks can capture that joint distribution and represent it. And what we can do is we can compare that joint distribution to the joint distribution of an alternative network, let's say Q. So now what is distinct between P and Q? In P, I'm highlighting a particular arc here that is part of the network P. In the network Q, that particular arc is absent, so that's missing. So so here, that's a network that's the same, otherwise only is missing the arc. So the Kullback-Leibler divergence now measures the distance in the joint distribution between P and Q. And what that does, that gives us a sense for the strength of that arc. So the more important the arc is, the greater the difference in joint distribution between the two networks. So BayesiaLab can do this automatically for us, and here I have this network again, but this time BayesiaLab has computed for us the numeric value of the Kullback-Leibler divergence. You see these little yellow boxes on the arcs, that gives you the absolute value, and below in bold and blue, you see the percentage value. So in this network, all the blue values, all the arc forces in percent would add up to 100%. So you may now ask, well, how is this going to help us with clustering? How is this useful for generating factors? Well, let's stick with this example, with this very simple model, just using, I think, 10 nodes here. This is how BayesiaLab would look at it. It takes the initial network and would consider each node, each manifest variable initially as its own factor. And then BayesiaLab would look at what is the strongest arc force in this network and create a virtual factor or virtual cluster and merge the nodes. So the two, in this case, green nodes, they would become one virtual node, and then the process continues. Then what is the next strongest arc? And then BayesiaLab would determine where that would be merged, and so on. So that's the idea, the agglomerative, I can never pronounce that word for some reason, this clustering approach that uses the arc force. And, you know, I have this slide in here, this wordy slide to be precise, but I think this is, again, best illustrated with a visualization. I'm showing you a sequence of screenshots. Later on, we will see something almost identical in the live demo of BayesiaLab. So here you see our network again. Now it's inside the mapping function of BayesiaLab, but I would like to draw your attention to the little box on the upper right-hand corner. In BayesiaLab, I have the clustering function turned on, which now allows me to choose the number of factors, the number of clusters. Here at the beginning, we're at the maximum of 10 factors, 10 nodes. Now going down one step, if I now say I want 9 factors, then the first merger happens, as I illustrated earlier. Now we have the big green node in the middle, which represents a merger between the two manifest variables. So now we have them merged into a cluster. And what I should point out, this virtual nuke cluster takes on the name of the strongest node within that virtual cluster as a temporary label. And this is really helpful, we'll see that later, that it's not just factor 1, factor 2, factor 3, when you really don't immediately know what that stands for, but as a temporary measure, any newly created factor carries the name of the strongest node, the strongest variable within that factor. So let's move on. Now we're at 8 factors, 8 clusters, and you see that, let me just see what, so how by going back and forth, you can see what has merged. And I just keep going here. Here we are 7, 6, 5, 4, 3, 2, and this obviously makes no sense. Now we have boiled everything down to a single factor. Now all the 10 manifest variables are merged into one. We can either show the short variable names, or here as an alternative, I'm showing the long variable comments, and this is obviously much easier for interpretation. But I've just now stepped through the methodology, what BayesiaLab does automatically in the background as we will perform clustering on our larger data set now. So, but now of course you may say, okay, but before we can do the clustering, we need to learn a Bayesian network, right? So in a way, we now need to rewind and go back to the beginning and learn the network properly, begin with the raw data. So we will machine learn a Bayesian network. I will briefly talk about the minimum description length concept in this context. Then we will do the clustering along the lines of what we've just seen. But then we will spend quite a bit of time talking about validation, concepts like log loss, contingency table fit. If we have time, we may be able to talk about cluster purity. But very important is visualization and interpretation that we will do at the end. So let me just talk briefly about learning. What it really means to learn a Bayesian network is to search for one, because there are many, many possible networks that could fit a given data set. Just to illustrate to you how big that task is, I'm showing you here 2 nodes, N1 and N2, and there are 3 possible networks that could exist for this particular set of 2 nodes. No arc, an arc from N1 to N2, or an arc from N2 to N1. So with 2 nodes, we have 3 possible networks. With 3 nodes, we already have 25 possible networks. In the case with our 240 variables, we would have a search space, a number of possible networks, 9 times 10 to the 9,000th, which is obviously a crazy large number that is impossible to explore even for the world's biggest computer. So how do we go about this? Well, BayesiaLab takes a very clever approach, trying to take countless shortcuts in searching this space, and different learning algorithms take different shortcuts to do this efficiently, hoping to find a well-fitting model. But what's important here that any candidate model that BayesiaLab discovers or tests is explored with regard to the minimum description length. That is the score that is computed that helps us to trade off fit and complexity. And here, I don't want to go into too much detail. The key point is that we measure the description length of the network to quantify complexity, and then we measure the description length of the data given the network to measure the fit of the data. That gets added up into a score, the minimum description length score. And the lower it is, the better the network, and the more likely it gets chosen by BayesiaLab as the final network. We can influence this a little bit by the structural coefficient alpha that allows us, if you will, to put our thumb on the scale. We can influence the degree of complexity. But today we will not do that at all. So I'll just mention it to be complete. This is what it would look like as BayesiaLab searches for networks. It evaluates many possible networks with the objective of reducing the score until it reaches the lowest possible score, which is returned to you. So with that, I will leave PowerPoint for a moment and switch over to BayesiaLab. So bear with me as I'm making the switch here. Okay, now you should be able to see BayesiaLab, the blue screen. That's how BayesiaLab starts up. I now want to bring in our data, our hexacode data set. So it's a large table, 240 columns times approximately 15,000 rows. The table itself is not very interesting because they're all recorded in exactly the same way. So during the data import, we really don't have to do anything. Now, here at this point, given that we have 7 states, we could now talk about whether we should leave them at these discrete levels or whether we should bin these variables further. Given that we have lots of observations, I'm voting for keeping those variables at their original discrete state. We have enough observations to work with this relatively fine granularity of levels. So I can very quickly skip through the data import process. We have no missing values. I'll go straight to the finish button, which now creates our internal representation of the original data. This should just take a few seconds here. Okay, so here are all our nodes, which each represent now one statement from the original personality inventory. I'll apply a layout, the staggered layout in particular, and I'm staggering the nodes here because now it will be easier to apply the long variable names that contain the statement from the original inventory. So for that, I'm opening a dictionary, a node comment dictionary. And now I can show the original statements from the inventory, such as I distrust people, I keep things tidy, I like order, I love luxury, I smile a lot, I speak softly, and so on. So all very straightforward concepts, but as you can see, very many of them and quite a few of them are quite similar in nature, reflect similar ideas. So, okay. At this point, we are ready for our first learning exercise, but let me bring all nodes into view right now. Now we're ready for learning, and given the number of variables, I think the best place to start is with a maximum weight spanning tree. That's a very quick learning algorithm, as you will see. Okay, in fact, we are already done with the learning. That's how quickly BayesiaLab has learned this network. As it appears now, of course, it is not easy to read. So I'm performing an automatic layout to kind of untangle this a little bit. And so now we have kind of this tree spread apart, and we could go straight in and examine it and look at the labels. But what I want to do first is repeat the exercise that we did earlier in terms of finding the strongest arc. Previously, you only saw screenshots. Now we want to do it on this live network. I switch into the validation mode. Let me just zoom out first. Go to Analysis, Visual, Visual Overall Arc, and select Kullback-Leibler divergence as the measure. So let me zoom in here. As we look closely at this network now, you can see that the arcs now carry a different thickness. Some are thicker, some are thinner. And I could also turn on the labels, which give us the exact numerical values for the arc force. But I want to kind of just for now look for the strongest arc. The way I can do it is scroll all the way to the right in this with this slider here in the upper right hand corner of the BayesiaLab window. And by moving it to the very right, I'm selecting the single strongest arc in this network. And perhaps you can see it. It is here on top. Let's see what nodes they are. It relates, or these nodes represent, I rarely cry during sad movies and I cry during sad movies. Perhaps given that they are opposite concepts and that people would answer them correspondingly, it's perhaps not a surprise that these are so strongly related. So that was the top arc. Now let me go one level down. And here at the bottom now, you see the second one is popping up. Here is the third. Next one, number 4, is here. I'm not sure you can see my mouse pointer moving around. Then number 5 is interesting because it doesn't start a new cluster, but rather that now attaches itself to an existing cluster, and so on. So we can keep playing this game until we're uncovering the weakest arc in this entire network. But of course, this would be quite tedious to perform if we had to do this manually. So what I'm going to do now is formally perform variable clustering with BayesiaLab. I go into the learning menu, go to clustering, and then variable clustering. Let me run that. And perhaps it's not so easily visible right now, but once I zoom in, upon performing variable clustering, you will see that each of the nodes now has a color. This is now the proposed cluster membership for each node. So what it means that BayesiaLab has now created 49 factors and proposed that the manifest nodes are associated with these newly proposed factors according to their color. So we could examine this here, just go look straight at the network and see whether this makes sense. But given that we have so many nodes, BayesiaLab has several visual aids that help you to evaluate the proposed clustering. So first, let's turn on our mapping function. And I will need to resize the window here a little bit so it fits within the space of the BayesiaLab window, because by default it opens up to the full screen, which may not be captured by GoToWebinar. So here is now my mapping view. here are my proposed clusters, and additionally, I'm also bringing up a dendrogram. This dendrogram gives me another way to look at the structure. So, okay, let me just make sure I'm sizing this correctly so it all fits within your screen. So the big mapping screen is now on the left, the dendrogram is at the right, and I can now interactively look at different degrees of clustering. So I'm moving the slider, the same that I used earlier for the arc force. I'm moving this back and forth, playing with the number of clusters. So as I'm now going beyond what was originally proposed by BayesiaLab, and that may be reasonable because I may have some domain knowledge about, perhaps I'm a psychologist, and think that certain concepts, even though they may appear from the data related, really are quite different. So I can now compare my domain knowledge based on the mapping chart as well as with the dendrogram. So I just go back and forth. And this is very helpful because even non-statistician, non-analysts, domain experts can look at this and really relate this to what they know about the underlying domain. It's a very intuitive way to arrive at a suitable number of factors or clusters. So I'll go back to what BayesiaLab originally proposed, and I'm closing that. So, in fact, let me now do one more thing. In fact, let me run this one more time with a slightly different setting now. And that is, from my domain knowledge, I determined that we don't want to have any more, we don't want to have more than 7 nodes, 7 manifest variables per cluster, per factor. So I've now set that as a constraint as the upper limit of numbers of nodes that can be part of a cluster. But beyond that, I may have not just sort of overall constraints, but I may say, you know what, a specific variable doesn't belong where BayesiaLab put it. In that case, I can go into the class editor. Hold on, I first need to actually confirm my selection. So I've now just confirmed these variables. I've accepted the proposed factor membership, and BayesiaLab is now saving these membership associations as classes. So here I have my list, my complete clustering report. So now I can go and show you what I was planning to show you, and that is if I now have some concern about, you know, what is in those factors, I can go in, open the class for the factor, and individually move and change membership. I can say this node goes out, the other one comes in for whatever reason. So I have complete flexibility in terms of factor membership beyond what BayesiaLab has proposed. But I'm okay with it as it is. I will now run, I will accept this clustering, which makes, actually, I'm looking here at my cheat sheet. Yes, there's one more thing I want to do, and that is testing the reliability of this clustering. Earlier on, I said, you know, we may get new responses to surveys. We, you know, perhaps we do a tracking study and collect data regarding the same questions, you know, once a month, so many times a year. in that case, obviously, we would want to find the same factors, the same clusters over and over again, and we wouldn't want to find different ones each time. So we would hope that there is some stability. So one way to ensure that these are reliable clusters is using our validation function here. And one of them that I want to show you is data perturbation, which now repeatedly learns a maximum weight spanning tree and performs clustering on that. So more specifically, I will ask BayesiaLab to learn this network 10 times, but with different degrees of noise added to the observations. So we're artificially creating noisier conditions, and that will perhaps help us uncover whether these nodes that we originally found are robust or not. So here's our report. It didn't take very long to produce. And first, I will show you here the variable clustering report. And I think this is a very helpful visual because it now shows us for each of the iterations what clusters were found and how consistently they were found. So here is our list of all variables, and if we scroll to the bottom, we can see how consistent, how similar each of the factor groupings are. And here's our summary score. So they are all in the 90% plus range. So even though the numeric code for the factor may differ between the columns, we can see that a lot of the blocks of variables are consistent. So basically, even though the factor number may be different, the same nodes are always grouped into the same factors. So that is very confidence inducing. But another way of looking at this, and this will now go way over the bounds of the screen here. So let me just try to fit this as much as possible. This is the frequency graph, the clustering frequency graph, that gives us a sense, or that gives us a visual sense of how consistently variables or nodes are grouped into the same concepts. And you can see those that have these solid thick lines that sort of stand by themselves. Those are apparently clusters or factors that are found each time with the very same variables. Then in other areas, you see there are some thin lines, which means there are some associations where sometimes certain nodes are grouped together, but not all the time. This is another hint for us to see, where we might have to add our domain knowledge to resolve any uncertainties about cluster membership. Okay, so let me close that. I am quite happy about this. So I think we can proceed with this clustering, or rather, because we haven't actually done the clustering yet, we've just found that we have defined factors, but now we really need to formally introduce these factors into the node. We need to create them and introduce them into the network. So that's what we do with the multiple clustering function. So, and there are many options to set here. We don't have nearly enough time to speak about all these options. One thing I need to do is find an output file, because during the multiple clustering, BayesiaLab will create as many subnetworks as there are factors. So I've defined a directory where BayesiaLab will put all those. But let me run this. This should perhaps take 10 or 20 seconds. BayesiaLab now has to create these factors and create states and values for each factor for each observations. So now, once this is complete, we have all the observations will have new, basically new columns, 55 new columns for each factor, and values for each factor. So we could later on look up what is the value for each respondent in terms of the factor. Let me open up just one of the factors to give you a sense of what they actually look like, how they have quite literally become manifest. I'm going to look up factor, I believe it was 17. Okay, so here we are. Hopefully you can see that now. Sorry that it took a few moments. Here we have our subnetwork for factor 17. So let me make this larger. So we have our manifest variables and our newly created factor in the middle. We can showcase the full variable names, and additionally I can also show in percent the contribution of each manifest onto the factor. But let me just quickly illustrate what that means in practice. Here I'm bringing up the monitors for the factor and the manifest. And here you can now see how the factor has states. And of course, the manifest variables have their original states. I can click through the states of the factor, and you can see how the manifest variables have corresponding values. So what this means is that the factor is summarizing the underlying manifest variables. So now what's interesting in this particular example is that, hold on, these manifests, they don't have the same sign with regard to each other. For instance, we have a statement that says, I worry about things. And then we have this one here, I rarely worry. So these are really opposite statements. So, and that's an important point here. It doesn't matter to us how these relationships, whether they're positive, negative, linear, or nonlinear, the factor can capture all of that. It's actually interesting to visualize. If we're doing a quick target mean analysis, we can specifically see how the manifest are related to our factor. And so here on the x-axis, we have the values of the factor. On the y-axis, we have the value, let me rephrase that. On the x-axis, we have the values of the manifest. On the y-axis, we have the value of the factor. And you can clearly see how the relationships have a different sign. Some are positive, some are negative. And what is very clear is that they are nonlinear. And that is important. And it's one of the biggest benefits of using Bayesian networks for factor analysis, because we can include relationships of all kinds. In fact, we can even use categorical variables and make them a part of factors. So I need to accelerate here a little bit so we get through our program. Now, of course, an important question is, well, how good is the quality of this representation? How well does this fit? And for that purpose, I need to switch back into PowerPoint real quick to share a few slides. Okay, so this is now a somewhat busy looking chart. What does it say? So it's about how can we measure the quality of the representation. So what BayesiaLab does for each factor and each set of manifest variables, it takes this Bayesian network model and plays all the manifest observations against it and computes the log loss. So on the left side of the slide, you have this table which shows the top 15 of the 15,000 responses. And for each observation, for each row, BayesiaLab computes the log loss. It basically means how well it fits the model. The lower the value, the better the fit. And if we take the entire column of the log loss values, we can do a histogram, which you see on the right-hand side, that shows us the distribution. So, which means on the left side, basically the left tail of this distribution, those are the well-fitting observations. Then those on the far right, they fit rather poorly. And now what is very practical here, we can now take the expected value of this distribution, we can take the expected value of the log loss, and that is the entropy of the data given the network. Now, we don't have to go into the theory here, and I'm just looking for where my corresponding, it feels like I've lost some slides are missing here that I wanted to show. I don't know where they went. My apologies. I thought I had a slide here that directly illustrated this point here, but now I can't find it. So BayesiaLab computes this for all factors, for all nodes, and can thus establish the quality of the network. And that's something we evaluate. And I'll now switch back into BayesiaLab. That's what BayesiaLab computes for the entire network. So this is our end result. Here we now have not just the subnetwork for factor 17, but here we now have 55 subnetworks with the factors at the center and then the manifest variables on the periphery. Let me turn off some of the labels to make this a little bit clearer. So we have all these little flowers and each represents a factor with the factor node, the factor itself being at the center, surrounded by the manifest variables. So, and we could now, depending on what our objective is, we could now perhaps identify a target node and turn this into a hierarchical model. Now, what I want to do in the last couple of minutes, and I'm sure to overrun my allocated 1 hour time frame now, one of the things I wanted to do here real quick, because with these 55 factors, we're now obviously way above what the hexaco model proposed with 6 factors. So what I'm thinking here, well, perhaps what we should do is see whether we can now find structure, build, learn a factor structure from the factors. So let's do just that. So we will perform a hierarchical clustering. First, and I'll explain in a little bit why I'm doing this. So I will now learn a network just utilizing the factors. So let me run a maximum weight spanning tree here again. Whereas previously we learned a network on the manifest, now we're learning it on the factors. So, and as before, we can perform clustering, but now clustering on the factors as opposed to on the manifest. And here now my objective is to see whether we can actually try to force 6 factors. So basically saying if we have the original hexaco model with 6 dimensions, what if we were to pursue a model with 6 dimensions? So we're forcing 6 factors. This is exactly what I'm going to do now. I'm boiling down these factors to 6 dimensions. Let me accept that. And now, once again, run multiple clustering. I'm just now kind of rushing a bit. Let me just do this. Okay, here we are. So I'll skip the clustering report. Here we now have our, oh, actually we have more than that. I must have selected the wrong number. So here it looks like we have 12 clusters. I apparently didn't adjust it down to 6, but for our purposes, that's fine. So we now have clusters of factors. But you see all the original manifests are detached. So what I will do real quick is I will reattach them with a ARC dictionary, what I saved earlier. So I'm now doing the layout again. And as I'm zooming out, now we can see the manifests connected to the first layer of factors, and then the factors connected to super factors each. So now this is perhaps a little bit tedious to analyze. So what is very helpful here in this context is our mapping function. In particular, the 3D mapping function comes in handy because now we can literally look at the hierarchy in layers. So our manifest variables are on the bottom level. They're kind of on the floor. And then on the first level up, we have our first level factors. And then at their center, we have the summary factors. And so that's how we can now explore this in great detail. In fact, we could save this through the Export 3D model button and create a virtual reality model that you can explore with your Oculus Rift. So especially for larger models, that is quite helpful when you have hundreds or thousands of nodes that you want to explore. But I think this now illustrates nicely how we can take a large number of original dimensions and bring them into meaningful structures that can be readily interpreted, in fact, interpreted through multiple layers until we arrive at the relevant concepts that are relevant to our line of study. So with that, let me do one final switch into PowerPoint. Okay. A few concluding remarks. First of all, everything that you've seen today, you can try out yourself, but please download the unrestricted evaluation version, or rather apply for it. This gives you the ability to load the complete data set that we're going to share with all 15,000 observations and 240 columns. Now, we will continue with our webinar program next week, not next week, in 2 weeks, on a totally different topic. We will talk about building a technical fault diagnosis system. And then what should be very interesting on July 27th, we will talk about adversarial reasoning and intelligence applications of Bayesian networks. So that should be a really hot topic, I think. Now, if this was of interest to you, please consider joining us for one of our 3-day courses. They are obviously much more in depth than what you saw today. We have the next one coming up in San Francisco. We've rented a fabulous venue. In fact, it's the former Federal Reserve Bank building in San Francisco, so it should be very nice. Then we have a course coming up in London, New Delhi, Chicago, and finally New York this year. Here's a picture of our venue in California, in San Francisco. And before I sign off, please let me invite you to our 6th annual BayesiaLab conference that will take place in Chicago this year, November 1st and 2nd. Before the main conference days, we will have a 3-day introductory course. After the conference, we'll have a 3-day advanced course, so you can spend a week with us all about Bayesian networks and BayesiaLab. We have a fantastic venue in Chicago right off Michigan Avenue, so I'm sure you'd enjoy spending a few days with us. We have folks flying in from all over the world, and the key point about this conference is really that it's BayesiaLab users presenting their work. So it's not us pitching BayesiaLab, it's rather users sharing their research projects. So this should be quite interesting, and I hope that I'll see many of you. With that, I apologize that it took me longer, much longer than expected, but I appreciate your interest. I would very much enjoy staying in touch with you. Here are my contact details. Please reach out with any questions. So with that, thanks again. I look forward to seeing you at a future webinar or seminar, and have a fantastic weekend.